the question that leads into this is, it's asking exactly the same question, but they just take the 0. They say, what power of 2 is a factor of 10 factorial? And you can say, oh, okay, 10 factorial. You get a number in your calculator, and then you can start to work with it and work out, oh, is it 2 to the power of 1, 2 squared, 2 cubed, etc. And you'll arrive at a number, okay? But then, see, this is what I was talking about before, right? They give you 100, which is like taking this, right, and just increasing the powers beyond the reach of what you can do by hand, kind of, okay? Your calculator can't accept 100 factorial. It just promptly says to you, math error. In fact, on my calculator anyway, my calculator can't even do 70 factorial. It just says, forget it. Which we shouldn't be surprised by. It is factorial after all. And when we introduced factorial notation, we saw how quickly it skyrockets. Okay? So 100 factorial, it's a big number. But here's the great thing, right? We are mathematicians. We are more than just calculators. We can do things that, how do I say this? I was about to say we can do things that our brains can't handle. You can consider things. You can consider things which, in the concrete, are too big to imagine, but abstractly you can still work with them. So let's have a go at this. What power of 2 is a factor of 100 factorial? Now, I want to come back to the original question, right, of 10 factorial. Okay. Now, what's this number? Let me just actually write down what the number is. 10 factorial. It's equal to this. Oops. Okay, now, this number is just barely big enough that you can work with this. And if I asked you to, for instance, give me the prime factorization of this number, think back to like year 7 or 8 when you had to define like greatest common divisor, lowest common factor, blah, blah, blah. You can break this up into all of the prime numbers, 2, 3s, 5s, 7s, etc. that are its factors. And you can do that uniquely, okay? The calculator will help you. But when you get to this, it's too big. So I want to use this as a case study that we can develop an approach that will work here, right? That we can bring to here. Now, if I just gave you this number, I said, okay, factorize, right? What would you do? Well, you'd punch the number in and you just start dividing by numbers until you got something reasonable. You'd say, oh, okay, I can clearly divide that by, say, 100. Okay, so you stick 100 over here, and 3, 6, 2, 8, 8 over there. And then you can say, well, I could divide up 100. What would you like me to divide up to? We can do lots of things. 25 and 4. Okay, that's good because it's 2 squares. And then you do this. You're like, okay, I'm not so familiar with this number. I can do. Let's see, 4 and something. Right, whatever it is.
907.
Okay. Sorry, say it again.
972.
Okay, there you go. And then you would just keep going. You just keep going. Except this is a silly thing to do if in fact you know that this number is 10 factorial. Because if I tell you from the outset that this number is 10 factorial, you don't have to monkey through this whole process. You know what all of these numbers are. Right? Because 10 factorial is in fact equal to 10 by 9 by 8 by 7, etc. Right? It's already been, hey presto, factorized before you even began. Okay? Now admittedly, like because you've got 10s and 9s and 8s there, which are non-trivial numbers, you do have to do a little bit of work. But not that much. Have a think about it. Let's go from the top. 10 is a factor of it's only 2 primes in it, right? That's 2 times 5. Right? 9, that's just 3 squared. 8, that's 2 cubed, right? You could do 4 times 2, but you'd have to go down again. 7 is prime. 6 is 2 by 3. 4 is 2 squared, and that's the last composite number. The rest are prime. Okay? So now I have my factorization sitting in front of me. I need to put it together a little bit, but essentially I'm done. Now remember, all I'm after, at the moment anyhow, is the powers of 2, the factors of 2. How many fit in there? Okay, this is not hard to count. 1, 2, 3, 4, 5, 6, 7, 8. They're all there, right? The factorization is given to you. There are 8, right? No more work. Okay, now hold on. This approach, this will work with this number. It will still be large, right? But it's doable. It's definitely doable. And there are things you can do to reduce this, right? You noticed I wrote out the whole 10 factorial, right? But I didn't really need to, right? Only some of its parts, there were 10 pieces. You notice I already skipped off. I only wrote down 9, right? I knew I didn't require the 1 because it's 1, doesn't add anything useful. But there are other numbers I could have cut out the process, right? I'm looking for powers of 2. I can reduce this by half, can't I? Which numbers should I cut out?
9.
Cut out all the odds, right? They're never going to contribute a factor of 2, right? So I take out this guy, take out this guy, take out this guy. Okay, now this problem is starting to become manageable. There are other things you can do which can speed up the process as well. Have a look here. You've got 2, 4, and 8, at least in this series, which are special, right? And you can work out very quickly what their powers are going to be. Let's see, I'll write them down here. 2, 4, 8, 16, 32, 64, and I don't need to do any more. Okay? How many factors of 2 will each one contribute? Well, this is going to give you 1, and this one's going to give you 2, and then this one's going to give you 3, and so on. Okay? Now, if I were just taking, like if I'd multiplied all of these numbers together, which I don't know what it's equal to, let's see, what is it? 6, 10, 18, 20, 21. Okay, so this is a big number, right? But I don't need to know what the number is equal to know what power of 2 will be able to factorize into it. I could just say 1, 3, 6, 10, 15, 20. Huh. Did that series of numbers seem familiar? Anyhow. There you go. Oh, 21? Sorry, it's a 6. So the 21 will fit into that. Okay? And then I've got all my other even numbers, so I'm going to have to add them all in. But that's okay. That's doable, all right? At the end, when you add up these and all of your other, let's see, what have I left in here? I've got 6, 10, 12, 14, etc. Okay, you can add up all of those as well. When you do them and you count out, you separate out how many powers of 2 you're going to get in there, well, you'll find there are 97. Okay, so that process, that's the unavoidable part. It does take a bit of time, okay? But it does sort out who's trying to do it the long way, right? The way that doesn't take advantage of what 10 factorial is actually equal to, 100 factorial is equal to, versus what's a logical way of actually going through this and trying to reduce the size of the problem. Does that make sense? Let's think about this. I have all my powers of 2, okay? But there are other numbers in the list, like these guys, right, that are not powers of 2, and they will contribute factors, right? More 2s, right? So how do I go through them logically without just listing them out? Let's think about this. I'll go from the bottom, the biggest numbers, to the top. You'll see why in a second. If there are any multiples of 64 within this number, it's a very, very big number. If there are any multiples of 64, they will contribute. I know exactly how many 2s they will contribute, right? For instance, if I said, just as an example, which I know doesn't work, but 3 times 64, what's that? That's 192. 192. Okay? Now, because I have told you that it's 3 times 64, right? That's 3 to the power times 2 to the power of 6, right? So I don't care about the 3. I'm only interested in the 2s, right? So this, being a multiple of 64, gives me the same number of 2s that 64 does. Does that make sense? I'll say it again, right? Being that this is a multiple of 64, and there are no more 2s that I can fit into that, right? It will contribute exactly the same number of 2 factors that 64 will contribute. Now, how many multiples of 64 are there underneath 100? There's only one, namely 64. As soon as you go to the next multiple, you're already too big. Okay? So I'm just going to say times 1. 32. 32. How many multiples of 32 are there? 3. Now, you can just do 100 divided by 32, and it's 3 and a bit. So there are 3, but don't forget, I've counted one of them already. Right? Right? So, in fact, there are only 2 left, namely 32 and 96, right? So I'm going to say there are 2 of those that I haven't counted. Okay, come to this guy. 16. How many multiples of 16 are there?
6.
There will be 6, but I've counted 1, 2, 3 of them already, right?
Oh, so there's only 3. Oh my god, this is so...
How many multiples? How many multiples of 8 are there?
4 plus 6.
No, answer the question for me. How many multiples are there?
12.
There are 12, right? Because I can go, let's count them out. Let's count them out. I can go 8, 16, 24, 32, 40, 48, 56, 64, 72, 80, 88, 96, and then I'm finished. So there are 12. 12? How many have I already counted?
6. So it's a sequence backwards.
No.
Wait.
How many multiples of 4? There are 25. How many have I already counted?
13. 12. No, I can't count.
I've already counted 12. So there are 13 left. Alright, last one.
That's not even
How many multiples of 2?
No, it's wrong.
There are 50. Right?
Those numbers are wrong. Doesn't fit our pattern.
How many do I have left?
25.
Okay. So, all of the ones that I haven't counted in here, they'll contribute 1 factor of 25. And these will contribute 2, and 3, and 4, and 5, and 6. Let's hope my numbers work. 25, 26, 18, 12, 10, 6. Okay, let's see. 30, 51, 16, 97. Thank you. I'm here till Thursday. All right. So look, see where the logic is. Resist seeing patterns 1, 2, 3, where there aren't necessarily patterns. Okay, and reduce down the question. Like, are you really gonna list out 1 to 100? No. You're gonna list out 2 to, like, etc. But are you really gonna list them out? No. There's a much more logical way to go about it.